Welcome to our workshop series on COVID-19 data analytics with Kubernetes. We are excited to bring to you a multi-part workshop series on building, deploying, and managing cloud-native microservices applications with Docker, Kubernetes, and Openshift. This workshop series is part of our ongoing Build Smart on Kubernetes work tour to empower developers to innovate more and ship faster with the leading enterprise container platform. If you're keen to gain the skills you need to propel your career into the world of microservices and container-based development, check out the Build Smart on Kubernetes work tour portal to access hundreds of online tutorials and events happening near you. Before we embark on this 8-hour-long journey together, let me introduce myself and the team so that you get to know us better. My name is Haghighi and I head up IBM's developer ecosystems across Europe. I'm fortunate to be working with an awesome team of developer advocates who are passionately engaging developers in various clients and open source communities. As developer advocates working for IBM, the pioneer of many technologies and inventions with a history of over a century, we have certain messages that we must get to the world as a whole. And that means to all developers all around the globe as much as possible using a special methodology: code, content, and community. We do that by being out there, speaking at various developer conferences, major tech events, digital channels, and contributing to many open source projects. At the same time, not only we do the outbound, but also the inbound. We have to be out there talking to users who's got their hands on the technology and get their feedback and their pain points and bring that information back to the product management team and the engineers to better improve the product, and the user experience is vastly superior to what it was. So that combination of outbound and inbound activities defines who we are and keeps us enthusiastic to make even better and deeper impact. Now, going back to our workshop, here's the agenda for the first series. As you can see, our agenda is literally the 7 pillars of cloud-native development, and the ultimate goal of this series is to teach you how to automate the entire application development process so you as a developer only focus on coding and eventually let Openshift take care of all the heavy lifting and tedious tasks. Or to put it in the developer's context, all you need to do is commit and push. Further, to simplify our learning journey and make it use case oriented, these workshops are designed around an application of a popular topic. Our application combines multiple containerized microservices for parsing COVID-19 time series data for the number of positive cases and mortality rates in different countries and regions. So you get to experiment with a variety of tools and technologies around a use case. Let's review our learning agenda. In this introductory part, we'll learn about cloud-native application development, the benefits of microservices architecture, and the motivation behind their vast adoption. We'll then take a quick tour of our COVID-19 application and how it's been designed. In part 2, you'll learn how to use Docker as the de facto standard to containerize and test your applications. In part 3, you'll learn about containers orchestration and how to deploy and scale your applications on Kubernetes. In part 4, you'll experience how Openshift simplifies and secures your orchestration task by automating the steps taken with Kubernetes in the previous part. We'll firstly use the CLI tool to deploy and scale our built containers, and later use Openshift Web Console to deploy our applications only using its source code with a few clicks. That powerful feature for developers is called S2I, or source to image. In part 5, we'll explore how code-ready workspaces helps teams build with the speed, agility, security, and most notably, code in production from anywhere. In part 6, you'll skip manage Openshift and instead use code-ready containers to build and test out your application, your Openshift deployment locally on your machine. And finally, in part 7, we will go even further with automation to set up CI/CD, or continuous integration and continuous delivery and deployment, to let Openshift completely take care of the entire process from development to production. Every lab in this series focuses on an essential step for building cloud-native microservices application. Well, you may ask, what is cloud native and how is that related to microservices, and more importantly, why developers should educate themselves on those? Cloud native refers to how an application is built and deployed rather than where the application resides. It basically defines that the application must be built, delivered, and operated in a way that it is not hardwired to any infrastructure. When I speak with engineers and development teams in some of the top firms in financial services, manufacturing, automotive, defense, medical, public services, etc., and I'm talking about major banks, pharmaceutical firms, and oil and gas, almost all of them host their solutions in multiple clouds, public, private, hybrid, and that's for both development and in production. For those firms, seamless migration from one cloud platform to another, being able to update their solutions with the latest technology and innovation, and scaling on demand with zero downtime whilst maintaining the highest security measures at every level are their top priorities. As you can see, those priorities are around the application itself rather than where it resides. And cloud native development provides all those benefits if implemented in the right way and using the right tools. For application developers and IT execs, here are the key drivers in adopting cloud native application development: improving application performance and reducing application downtime and associated costs, quicker development and rollout of application enhancements or new features, easier application management, and greater flexibility to scale the application resources up or down automatically to meet real-time changes on demand. And the adoption. Over half of the new applications to be developed in the next year will be on cloud, and among the current adopters of the model, 53% of the applications are cloud native. But more importantly, IT execs consider cloud native app development as the key driver for cultural transformation for their tech teams. Including small teams own specific components of the overall application. Collaboration between application developers and IT experts are enhanced, and continuously and centrally integrating source code operates across the team. And that basically creates a pipeline that deploys apps in development, test, staging, and production environments. Now, how does cloud native development make those happen? Simply by relying on microservices architecture. Microservices architecture is the building block and the most essential ingredient of the cloud-native applications. A cloud-native application consists of discrete, reusable components known as microservices that are designed to integrate in any cloud environment. In its core, the microservice architecture advocates partitioning large monolithic applications into smaller, independent services that communicate with each other by using HTTP and messages. Take a look at the conversion of this monolithic business application into a number of microservices according to their business capabilities. These microservices act as building blocks and are often packaged in containers. Microservices work together as a whole to comprise an application, yet each can be independently scaled and continuously improved and quickly iterated through automation and orchestration processes. The flexibility of each microservice adds to the agility and the continuous improvement of the cloud-native application. Here we've got a business application with a single database server, and this application's got all the functionalities such as the storefront, catalog, recommendations, inventory, and billing all packaged together in a single unit. If any one of these functionalities fails, the entire application will become unresponsive. Whereas on the right side, we have basically broken down the application into multiple microservices. Each one of these services, such as billing and inventory and the catalog, is gonna basically scale on its own individually according to demand. And that basically helps the application to scale according to the need. And also, it would basically help the teams to update and develop new features for each one of these services individually. And this is one of the most important advantages of microservices architecture. Before we dive deeper into microservices, let's take a quick look at the type of application used to be developed in the traditional way, or as we call it, monolithic applications. In the old days, when agility, time to market, and rapid application deployment weren't as vital as they are today, developers built a product and add features to it over time. As new features were added, the application grew bigger and bigger in size and complexity. That model was destined to fail because Applications were built to run on VMs with a massive operating system, libraries, dependencies, and a single database attached to the entire application. As demand grew higher, scaling the application was literally spinning up new VMs and adding more machines to the infrastructure. Different services in the monolithic applications were tightly integrated, and failing one part of the application caused the entire application to become unresponsive or unusable for clients. Failures aside, when making updates, performing maintenance, or adding new services, the entire application must have been rebuilt and deployed again. If new updates happened to cause the application to fail over time, the entire application had to be brought down in order to fix the problem. Identifying and fixing the error was a tedious process and never guaranteed to succeed in a short amount of time. On the other hand, developers who worked on a project together often had to program in the same programming language and use common platforms and tools to keep their individual parts compatible with others. Scaling a single part of the monolithic application in most cases wasn't possible unless deployed on a separate VM. That required the entire application to be updated with additional resources for the entire application instead of individual services. That is not all. Monolithic applications also disrupted teamwork and prevented collaboration between developers and operations engineers. There always existed this massive tension between the two teams, pointing fingers every time something went wrong. Developers used to blame operation engineers for not having a thorough understanding of the architecture and causing their code to break, and operations engineers used to blame devs for delivering something which was not scalable, ready for production, and demand too much underlying resources. When you look at it from the developer's perspective, they often spend their days building something new or debugging something that's broken, which is why they want a solution that simplifies the development process, making it faster and easier. The faster they can improve existing apps or find errors in the code, the more time they have to learn new skills. And that is why orchestrated containers, microservices come to their rescue. The benefits of microservices, agility, shorter development time, flexibility, help developers build something more robust, faster, and with fewer problems. And those are CI/CD, making decisions for each microservice according to the technology stack that best fits for the purpose, helping to address zero downtime, and develop and evolve components or services on different timelines. Those are the top benefits for developers. This is how our course is going to teach you the steps involved in cloud-native development. I've already broken down the monolithic application I had designed initially into multiple microservices written in different programming languages. And then we're going to use Docker to containerize each one of those microservices. And then we're going to basically orchestrate them with Kubernetes, Openshift, and code-ready containers. So you'll learn all the scaling, managing, and deploying of those containers using those platforms. Later, we're going to take a look at code-ready workspaces to deploy your application just using the source code from your Git. And that is a very powerful feature of Openshift container platform. Before we view the application, here's a quick summary of the architecture and components. Our application has been developed in Java and a Spring Boot framework. It provides us with a number of API endpoints for retrieving COVID-19 data per region, country, data, and periods. As you can see from the slide, data is fetched from Johns Hopkins University repo, which is an authentic source of COVID-19 and is stored in our local data repository and can be viewed from a front-end UI which runs as a microservice. Our application is consisted of a number of containers microservices, including 2 data parsers for positive cases and mortality rates per country, and a user interface for displaying data and invoking those APIs through a number of sample functions. Here we've got our Openshift cluster on IBM Cloud with our microservices running as individual pods. We've also got a load balancer that directs traffic to our pods from external networks or the internet. Here's the list of sample API endpoints as we will test them out shortly and throughout this series. Both applications are open source and can be accessed with full instructions on my GitHub. Now let's take a look at our containers Java application stored in IBM Cloud Container Registry and running on managed OpenShift on IBM Cloud. Let's get started. Here's my OpenShift cluster on IBM Cloud. As you can see, I've got the pods, as I had mentioned to you. So these applications, I haven't actually connected them together, so they're all available as a standalone services. So I can connect to each one of them directly and take a look at what sort of functionalities they provide. I mentioned to you about Johns Hopkins University and the sort of data repos they provide for COVID-19. So if you go on coronavirus.jhu.edu, you basically get a link to this page, but if you want to come directly to this page, is map.html/map.html. You can see a lot of visualization of data here, lots of good information, useful information, and some stats about the recent death and positive cases around the globe. What we are interested in is basically going to the source of data. This is obviously just a visualization. The source of data is on GitHub, on their own GitHub repo. So if you go on github.com CSSEGISAND data, you can basically get to the COVID-19 data. The link is going to be available under the page, so you can browse to this page. So once you go into their GitHub repo, we've got different folders. So the ones that we're going to look at is COVID-19 data, CSSE COVID-19 data. Once you go in there, you've got a time series data. That's exactly what we are interested in. Those are live data, getting updated every 5 to 9 hours, as you can see here. So they've got a specific one for global cases, confirmed cases, and a US confirmed cases, and also death cases in the US and death cases globally. Let's take a quick look at what basically the confirmed cases look like globally. That is a CSV file, but obviously this has already been parsed. If you want to look at the CSV raw file, it is something like this. So it is not readable easily. So this goes for all the data confirmed cases from around the globe. If I go back, you can see that the first row is basically it shows the lat long and the dates, just the headers for our table, and the first column is basically the region. So not all countries have regions or provinces or states. And then the second column is basically country, and then latitude and longitude. So our application basically connects to this repo, retrieves this data, this raw data, and then parses it and make it available through a number of REST APIs. Now let's take a look at our application. As I said to you, this application runs on OpenShift on IBM Cloud. So I'm going to use my CLI to connect to my OpenShift cluster. Let's get my pods. So these are the pods that I've just shown you on the UI, and I'm going to get their IP addresses. So I've got one pod for the death cases, the other one is for positive cases, and another one for the UI. There's also another one for code ready workspaces and Kubernetes, which doesn't matter. We're going to get to that shortly. But the external IP address for my UI app is 169, is this basically. So the external IP address for my UI is this, and then I've got it on 32248. So let's go ahead and if I'm not mistaken, that's right. So now we are connecting to our user interface. This is the user interface hosted on OpenShift on IBM Cloud. It's a simple user interface just to show you what we can actually get from our parser. The first step here is for me to connect to my parser. This already runs inside the same node and an Openshift cluster. But I'm going to use the positive cases. So in this case, I'm going to use the public IP address rather than just using the in-cluster IP address. But I'll show you shortly how that works as well. 32059. So let's see. So now it basically connects to my parser, but it's not within the cluster, as we will see shortly. So here I am. I'm going to basically display data for all countries. Just play on load, press on load, and then if I go down there, I can see all data for all countries showing up there. Obviously, the data is massive. It's not going to be able to show everything in that table. What I'm going to do is I'm going to display all data for a single country. In this case, let's choose Argentina. That's the data for Argentina for all the positive cases from the 22nd of January all the way to the 5th of July. And also I can basically say for all countries on a specific date. Let's see what all countries data look like on the 30th of June. So starting from Afghanistan, Albania, all the countries are sorted alphabetically. As you can see, like, these are the number of positive cases globally for every country based on the regions as well. For instance, when we look at China, we can look at it per region, and it goes all the way down. You can see it. And also, if you want it for a specific date for a country, you can do the same thing. If you want it for a period, so again, if I go for, like, let's say Brazil, from the 1st of June until the end of June. Let's see what the data will have. So now we've got all the data for the positive cases in Brazil. You can see it starts from 500,000, around 500,000 on the 1st of June, and it goes to nearly 1.3 million positive cases by the end of June. And as you know, right now it's actually one of those countries that the viruses are spreading rapidly. So this is just our application, basically a quick look at our application, just to show you what sort of functionalities you can make available. And this runs as a microservice, so you can run your own analytics, microservices analytics as well within the cluster, and parse data and analyze data. So that was a quick demo. Let's take a look at what it's like to just access it through your own browser. So if I just get this, so we were connected to, so for our positive cases, this is the IP address, and then 32059. So I've got a REST endpoint saying hello. Let's see if we get, yeah, hello world. I'm going to get the country data, country data, and then let's pick a country, Albania. So this is all the data for Albania. As you can see, we've got it per date, what sort of number they have for positive cases, and it goes all the way till the 5th of July, as we had seen. So basically you can design your own application and just invoke these REST points. The other one is if I want to just curl it through my my CLI, I can just go ahead and Docker v59, then hello, so it should work. Hello world. And the same goes if I want to get a country data, and let's look at Albania again. That's all the data coming through my CLI. So super simple. Whether you've got the UI or not, you can basically go ahead and connect to the application, and that's how we're going to look at it. But the beauty of this application is it is scalable. Given that it is running on Kubernetes and Openshift, it is scalable. So the system is going to scale this no matter how many visitors or how many people are going to invoke the REST APIs. The system is going to be able to cope with that because the infrastructure, the platform is elastic, and Openshift is monitoring all the services at all times to make sure that your services are always available and you have zero downtime. Now let's go back to our slides. So that was a quick demo. I hope you have enjoyed the demo and it's interesting to you. But when you look at the architecture, for the application, we've got the data parser, we've got the build database sort of functionality, and then we've got JPA, as I'm going to show you shortly. So JPA is for storing data. That's our persistent module, and then our REST APIs basically come after that. And the entire application is running on Spring Boot. So we've got two sides. One side is basically data retrieval, and the other one is data availability through the REST APIs. If you dig deeper into the application, we've got a data source and data parser. So those two are the major components here. Data source defines whether this data is coming from a URL or coming from a local file, and it is in CSV format. The second part is a data parser that gets all the CSV data and then parses it based on different countries as key values for every country, and then the data set for that country, and that basically becomes our entity. So our entity first entity is a country with name, lat, long, and the data sets, and in every country object we have a data object that stores all the data for that particular country. Our repository, in this case, we are looking at it from the Spring Boot perspective, those annotations. Our repositories are JPA repository, and then data repository basically implements that. Our REST controller, we've got one side our internal REST controller basically, so those are just functions that make data available to the rest of Java application, and then we've got the REST controller for the APIs. As you can see here, so if you've got it running on your own local machine, you can get all the data from, for instance, port 8082. That's the way I've basically designed this application. At the moment it's on 8082. You can change it to any port, and then the REST APIs are designed in a way that you get country data, get country data date, for that particular date, so you can feed that data in, etc. When you look at the design of this application, it gets a little bit complex. So that's why I've dedicated a complete course. It's about 2 hours basically, to show you how you can design and build your application, Java application, and using a Spring Boot from scratch. And that's in with Maven framework. For the first part, we design a simple CSV to JSON parser, then we add objects, gradually add authentication and JPA repository, like kind of the sort of foundation required for that. Later on, we look at what sort of dependencies we need, and the annotations you need to inject into your application. Also, what sort of REST methods you're going to use, and how you're going to basically connect to your REST controller, and how you design your REST controller. So I'm using REST template. You can go ahead and use web client to make your application reactive. For the time being, I'm sticking to REST template for simplicity. And then last but not least, we're going to look at databases and why databases and how databases need to be designed and managed for a Spring Boot application. So that's a separate course, but these are the steps you need to design this data parser that I've just demonstrated to you. Throughout this course, the way we're going to look at this application is from the microservices standpoint. As I told you earlier, we've got every microservice running in a pod within our Openshift or Kubernetes cluster, and each one of these pod or microservices, each one of them is basically independent, decentralized, based on functionality. So they're designed based on functionality, a specific functionality. So the data parser is just a data parser, it doesn't do anything else. Our data analysis is basically just a Python program for analyzing data. Visualization is the same, and the user interface is exactly the same. So those are the sort of characteristics for microservices that you need to follow to make your microservices functional and according to the architecture. So those are basically the best practices, and they all have their own persistence module. So in this case, the data parser, as you had seen, it's got its own database, and they're also deployable, independently deployable. Again, that is important. They're not tightly integrated or tightly coupled with any other modules. And also you need to run tests to make sure the services that you including your applications are resilient. But when we look at it from the cluster perspective, breaking down your application makes it possible for these applications to be accessible from outside your cluster or within your cluster on their own ports and addresses. So they are independently available as well, and you also independently scalable. Let me put it this way. So in future parts of this lab, you're going to see how you can create replicas for each one of your pods and each one of your services, and your service can scale. So this way, when you have your application broken down into smaller pieces, each one of these, when the demand goes higher, they can basically scale without affecting the rest of the system. You don't have to scale your entire application. You can just scale those services that are in demand, at high demand basically. One more demo that I'm going to show you here is basically I'm running two instances of my data parser, as you had seen previously. One is for positive cases, the other one is for death cases. And the beauty of microservices is that, for instance, I can just create a second instance of one of my services and connect it to a different source, and then my UI as another microservice can alternatively connect between either to this one or that. And this is quite interesting because I'm basically creating my application once, but then when it comes to the data retrieval, my user interface can decide between these two data repos. And at the same time, if I've got my analytics, my analysis, data analysis microservice running, that can do the same thing. It can basically go to each one of these pods and get the data that it needs. Just to give you an idea about the sort of API endpoints we're talking about, here's the list of API endpoints. It's already available on my Git, so you can go ahead and take a look at it. But for the one that I just mentioned to you about the positive cases and death cases, let's take a look at a quick demo and see how that works. So you remember here that I basically, when I got my services from my Openshift cluster, I have one for positive cases and the other one is for death cases. So far we've only used the one for the positive cases. Let's take a look at what it's like for our death cases as well. That is on port 31051. So if I reset, and then this is on 90. 31051. So let's connect to that. So now I'm basically connecting to the death cases on the repository. So this is now, from now on, I'm looking at the country's death rates. Let's look at all, display all data for a country. In this case, I'm going to go ahead and pick Brazil. So as you can see, like back in January they had 0 death, but as we go along, this number is going higher rapidly. So right now, back in on the 5th of October, on the 5th of July, they had 64,000 deaths. Previously we looked at the positive cases, and that was 1.3 million if I remember correctly, and now you're looking at the death rate, and this is exactly what the data looks like. Now let's look at the display data for a country on a specific date. So for instance, if I'm going to look at the 30th of June, so that's 59,594. For Brazil, between the 1st of May and the 30th of June, or let's take a shorter period, 31st of June, 31st of May, let's take a look at it. So that's the data for that specific period. So if you have designed an application, you can just look at that specific period for the data and then compare it with another country, for instance. So that is the beauty of having microservices and having 2 parts available, but it's the same application. Basically what I've shown you here is a public IP address. So my application, even though it is in the same cluster, it goes all the way around and then invoke the application through a public IP address, whereas I can easily connect my UI to my application within the cluster. So let's reset and connect again. This time I'm going to get the cluster IP. So this is the cluster IP for the death cases, and it's on the same port. Let's look at it now. Parser is not responding. Let's see what I've got wrong here. So I've got my cluster. Oh, that's my Parser, that's right. 31.0.1.1. It's much work. Oops. I think I've got my I made a mistake. So I was basically trying to access my pod with the port number that was publicly available outside the cluster. So I can just go ahead and use the port number for the container that is exposed outside the pod. So it's 8082. So that's the way I had deployed my application. So you basically get the same service, but now within the cluster. So let's take a look at Brazil again. As you can see, like the data retrieval is much faster now. It's because we are not going to make a loop, through external IP addresses and then coming in through a different DNS. So now it's basically all happening within our cluster. So again, this is the data for Brazil. So I just wanted to show you what it's like for your applications, basically to connect, for your microservices to connect together within the same cluster, and that's basically how it works. So just to provide you with a quick demonstration of what actually happened. So we have the same application running. One is retrieving positive cases, the other one is retrieving death cases, and making them available exactly on the same API endpoints, but on different port numbers. In this case, when we connect from our user interface, we need to use the port numbers. We've got different port numbers, port names basically. One is node port, container port, and the port. So we're going to go through that shortly. So you will learn all the details of different port numbers in Openshift and Kubernetes cluster. But that's the way it basically works. Here's what we've learned together during this workshop. We explored cloud-native application development and discussed its advantages. We talked about microservices and why microservices are superior to monolithic applications. We took a tour of our COVID-19 data analytic app and its API endpoints and some of the architecture, including its architecture on Openshift on IBM Cloud. Here's the rest of our journey and what we are going to learn together throughout this course. Stay tuned. See you in the next lab.